Hello everyone, welcome to our presentation. Today we will talk about our effort to the 2020 IWLS programming competition. As shown in the title, our approach is to learn Boolean circuits with machine learning model example. My name is Yuan Zhou. Our team has 5 members: me, Jordan Dozel, Yichi Zhang, Hanyu Wang, and our advisor Zhu Zhang. Hanyu is from Shanghai Jiaotong University and he is doing a remote summer internship in our group. The rest of us are from the Computer Systems Lab at Cornell. Before we dive into the details, let me first give an overview of our approach. As mentioned in the previous slide, we use an example of machine learning models to learn Boolean circuits. Specifically, we use an example of 3 types of models: decision tree, random forest, and multi-layer perceptron. For each type of model, for each benchmark, we perform a grid search on the hyperparameters of the model. Since we can obtain the validation accuracy and gate count from ABC during evaluation, we can get the best model of this type after the grid search. We do the grid search for each model type, get 3 different models, and select the best one as our final result. Our approach can achieve 87.4% average accuracy on the provided validation set and 87.3% on the test set as measured by the contest committee. Let me first introduce our binary decision tree model. Here I am showing an illustrative diagram of a binary decision tree. At each non-leaf node, the tree evaluates a certain input value and decides whether it should go along the true path or the false path. This process repeats until a leaf node is reached, and we will get the final prediction here. When training the decision tree at each non-leaf node, we use entropy as the impurity function and select the feature with the maximum entropy gain. The formulas are shown here. Converting such a binary decision tree to a circuit is very straightforward because each non-leaf node can be represented as a 2-input multiplexer as shown in this figure. The leaf values are just constants and can be directly fed into the multiplexers. In the previous slide, we described the vanilla binary decision tree. When we were using such trees on the contest benchmarks, we found that the trees often do incorrect splits at the beginning because of insufficient training data. For Boolean logic, it is very likely that a correct split has no entropy gain at all. It is most intuitive if we think about a 2-input XOR. In this case, only using entropy gain to select the splitting condition will cause the tree to ignore the correct variable and be misled by the sampling noise. To solve this problem, we integrated single variable functional decomposition into our training algorithm. This functional decomposition is triggered if the best entropy gain we found at a certain node is below some threshold. We determine that we can split on an input with functional decomposition if either of the 2 cases shown here is satisfied. After the split, either one branch is constant or the 2 branches are complements of each other. Because of the limited amount of training samples, we use an aggressive strategy. We will always assume we can split by functional decomposition unless we detect any contradictory sample. Now I will hand over to Yichi and he will talk about the random forest part.
We also have random forest in the model ensemble. The random forest contains multiple binary decision trees, and each of them generates its own prediction independently. And finally, we use a majority vote to generate the final prediction. When converting to the circuits, we use the same method as for a single binary decision tree for each tree in the forest. For the majority vote, we generate the truth table first, and then we convert the truth table to the circuits. Next, I'll pass to Jordan to introduce our MLP model.
The next model in our ensemble is a multi-layer perceptron. It has a simple architecture with 3 layers. The first layer receives the input bit width, and then the later layers decrease their size by a factor of 2, with the last layer just having a size of 1. This model has ReLU activation and bias. We enumerate the input-output pairs to generate a large truth table, which we then pass on to ABC for minimization. This method has the advantage of abstracting away all the internal details of the model, yet due to the exponential nature of the input space, it is only feasible for the smallest benchmarks. We found with our experiments that it is difficult to learn periodic features using ReLU, so we looked for alternative activation functions. The activation function that we eventually used in our ensemble is the sine wave. And the sine wave has the attractive features that in its nonlinear region for larger activations, it could more easily learn periodic features within the input data. And these features can vary by frequency, which it could learn just by adjusting the weights of the network. Also, if the activations are small enough, the first order linear approximation is just the identity function, making the activation function monotonic like the rest of the standard activation functions currently used. Here are the results of the multi-layer perceptron with ReLU and sine activation. The y-axis is validation accuracy and the x-axis is the benchmark ID. You could see on benchmark 74 and 78, the sine activation performs much better than ReLU. And on the other benchmarks, they perform fairly the same. Now I'll pass it over to Yuan for further results.
Starting from now, I will briefly discuss our results on the context benchmarks, as well as some comparisons against other techniques. Our first observation from context benchmarks is that, despite being a simple model, binary decision tree performs pretty well in many cases. Here I am showing the results on benchmarks 0 to 19. The y-axis shows the validation accuracy and the x-axis shows the benchmark ID. As we can see, binary decision tree achieves the best result on many of them. Although not shown here, we also observe that functional decomposition helps avoid noisy splits on many of these benchmarks. Our second observation is that random forest works the best for benchmarks with large number of inputs and complicated logic expressions. This figure shows the results on benchmarks 80 to 99, where benchmarks 80 to 89 has 196 inputs, and 90 to 99 have 768 inputs. Random forest consistently achieves good results on all of these benchmarks, showing that we need higher model capacity to correctly learn the logic functions of these benchmarks. Our third observation is that MLP with sine activation achieves perfect accuracy for benchmarks 73 to 79, as mentioned by Jordan in an earlier slide. Finally, for some benchmarks, none of our models is able to learn the function. We are not sure about the reason, but probably the functionality of these benchmarks are very complicated and cannot be effectively learned from 6.4K training samples. We also compared our approach against several other techniques. The first one is espresso, a classic logic optimization technique. In this figure, we are comparing binary decision tree and random forest with espresso, where the y-axis is validation accuracy and x-axis is the benchmarks. The benchmarks are sorted according to increasing accuracy of espresso. As we can see, espresso has a similar accuracy trend with the binary decision tree, although binary decision tree is better. Intuitively, we believe this behavior can be explained by some intrinsic similarity between espresso and binary decision tree. While espresso exploits don't cares by expanding minterms, as shown in this cardinal map example, the binary decision tree exploits don't cares by performing cuts in the input place. One example is shown here, where the decision tree exploits the don't care in the blue split over here. As a result, neither espresso nor the binary decision tree can learn the Boolean function if such a nearest neighbor property does not hold for the function. In the extreme case, if the zeros and ones are completely interleaved in a cardinal map, which I believe should be the case for parity function, for example, then neither technique can learn the function unless the complete truth table is given. We also compared against the lot network approach proposed in this ICML-18 paper, which is linked to in the contest handout. In the figure, the benchmarks are sorted by increasing validation accuracy of the lot network approach. The curve of the lot network is sort of similar to random forest, showing that it is a relatively high capacity model. However, we observe that the lot network rarely gets perfect training accuracy, which means that its randomness prevents effective learning from the training set. So that's all of our presentation, and thank you for your attention.